Welcome back, everybody. It's been quite a while, and I apologize for the wait, but I finally am adding another video to this AP Physics series, and today it's going to be about momentum and kinematics. So let's get right into it. Slightly different style of video today, and I hope you enjoy. So let's assume you're just having a nice day. You're walking along this nice orange salmon pink brick road, but all of a sudden, out of nowhere, you see this block. It's a green block. It's falling from the sky, but it gets stopped. It gets stopped, and below it, there's this blue block that slides in. And these two blocks, they both have a mass of 10 kilograms, but the top one, it's stopped. It has no velocity. And the bottom one, it's going to get launched up at some velocity, as these arrows indicate. The green one's going to fall. And the question is, if they're 1 meter apart, which is really peculiar, if we're going to drop this, the question is, if they collide inelastically so that they stick together, what should the velocity of the bottom block be such that after this collision, they can return to their maximum height of 1 meter? And this is a very interesting question, and I encourage you to pause it and take a second to figure it out yourself. If you are able to figure this out, I would think that you are quite well prepared for the AP exam, especially in this specific portion. So if you can solve this, I don't think any of the momentum questions will really be too tricky for you. This is pretty conceptual, but it does involve a little bit of algebra, so just manipulation numbers. So I'll give you a second to pause the video and see if you can do it. We're gonna just take a look at the diagram if it helps. And so now that you've given it a second to pause and figure it out, hopefully, let's see if you got it right. I think when looking at a question like this, it's important to split it into two parts. There's something that happens before the collision, and there's something that happens after the collision. So before the collision, they're going to have to collide at some height and at some time. So when and where do these blocks collide is a very important question I feel like you should ask yourself when solving this question. And then after they collide, how far do they travel together? Because these two phases are distinct. The first one is two separate objects colliding towards or traveling towards each other, and then after the collision, they are now one continuous object, essentially. They have stuck together, they've collided completely inelastically. So, given this, let's zoom in on each block individually. Here's our green block. It has that arrow, it's falling down. And in order to determine its location in space, we're going to use a kinematics equation. This is given on your AP equation sheet, but I would recommend you understand how it works, and I hope that going into this video you already know how to use this. This is obviously the position function. It's going to be the initial position, x naught, plus v naught times time, plus 1/2 at squared. And this is, of course, during a constant acceleration type of motion. For simplicity, I'm going to say that the positive direction is upward towards the sky, and then the negative direction is going to be downwards towards the ground. We can start by seeing some variables that we know. We know that the initial height, the x naught, is going to be 1 meter. And we know that its initial velocity is 0, because it's being dropped from rest. We're going to assume that a is g, because it's under the influence of gravity. And we're going to say that g is negative 10 meters per second. Negative because it's pointing downwards, and then 10 because I'm lazy and it's much simpler. So if we throw those to the side real quick, we're going to come back with a simplified version of our equation where we have x of the green block is 1 plus 1 over 2 gt squared. We're going to plug in that g, which is negative 10, and we're going to get x of t for the green block is going to be 1 minus 5t squared, and it's this nice algebraic expression we can work with. There's no units, we know it should be in meters, so the dimensional analysis works out, and for now, and from now here on out, we're just going to not use units, which is arguably not a good practice, but it's good for simplicity. So going back, now that we've seen our green block, let's look at our blue block. We know that x of t is going to be its distance above the ground. For both the blue block and the green block, we can use an x of t sort of diagram. Obviously, the function x of t is going to be different for the blue block and the green block, but they both have this position function that can be defined as a function of t. So looking at our blue block, if we use the exact same original kinematics equation to start off, The only thing that's different is that it doesn't start at a height of 1 meter. It starts at the floor, and then it also has an initial velocity upwards that we're going to give it. Other than that, a is still g. It still points downwards at 10 meters per second squared. So if we plug it in, we're going to get VIT plus 1 over 2 GT squared as our position function for the blue block. And of course, VI is this value that we're trying to solve for in this question. Doing some plugging in or substitution, we're going to get that the position of the blue block, xb of t, in terms of t, is going to be vi times t minus 5t squared. And remember that will be important. So, going back, now that they've collided, what has happened? We're moving on to the second part of our problem. Now that we know that's a certain distance above the ground, we can find this t. When do they collide? So we know the two positions. So if we just set the two position functions to each other, so x of g and is x of b, they should be occupying the same space, which isn't really possible, but for the sake of the question, that's when they collide. They collide when their position functions are equal. So if we plug in the two values that we found, or the two algebraic expressions we found, we have 1 minus 5t squared is equal to VIT minus 5t squared. And really conveniently, the 5t squared will cancel out, giving us 1 equals VIT. And we can just divide VI to get the time of the collision is equal to 1 over the initial velocity of the blue block, which is what we're finding. And some of you might be confused or thinking, okay, well, that doesn't really help us because we're still trying to look for VI, but just trust the process. This is important. So keep that in the back of your pocket. The time of the collision is equal to the numerical value of 1 over VI. So going back to our two blocks, they've now collided. They've collided at this distance above the ground. So we have this x of t function, which is the distance above the ground. And we can choose either x of the green block or x of the blue block. And I'm going to go with the green block because it doesn't have the VIT in the front. It just has a 1. So if we plug in t equals 1 over vi for the x of t function, we can find the height of the collision, this h collision, is equal to 1 minus 5 over vi squared. And that will be another value to keep in your back pocket. So going back to this question, we split it into two parts. We know there's a total height it has to reach. We know that there's this height of collision plus the distance they travel together after, totaling to that total height. And if we know the total height is 1 meter, that's really helpful because we've just now solved for h collision. It was that 1 minus 5 over vi squared value. So now we just need to find the arguably more difficult value, which is the distance they travel together after. And if we use our principles of conservation of momentum here, it's actually not too difficult. So if we look at the two blocks together, they're this one object now that we can think of with a total mass of 20 kilograms. And I'm going to say that they're traveling at this final velocity, just v final. And if we use our conservation of momentum, we have the initial momentum is equal to the final momentum. And final momentum is pretty easy to just algebraically write out. We're going to know it's the final velocity times the total mass. And we're going to plug in 20 for mass total just to keep it simple. So it's 20 v final. But the momentum before is the one that's a little more tricky to find out. Because although we know that mg and mb are 10, and we can just plug those in, we don't know what vg and vb are. So in order to do this, we're going to need to go back to the blocks and do some more kinematics work. So going back to this green block here, we can use the kinematics equation for velocity, where it's just acceleration times time plus the initial velocity. And if we just plug in that the initial velocity was 0, and we know that a was g, which was negative 10, we know that the velocity of the green block at a given time t, which was t collision, 1 over vi, by plugging in v of g, by plugging in t collision into v of g, we're going to know that g times vi is going to be this velocity at the collision point. So if we plug in the negative 10, we're going to get this value negative 10 over vi. One more value to keep in your back pocket. If we take a look at our blue block instead, we can use this exact same original kinematics equation, but we're going to do it for the blue block instead. This velocity, VB, is going to be V0 plus AT. We know V0, it's going to be VI. It's this value we're solving for. It shows up a lot because we're looking for it. And then A is obviously going to be G again, which is negative 10 meters per second squared. Once again, we're just going to say it collides at some t called t collision, which we found to be 1 over VI. Plugging in t collision to VB, and we're going to get VI plus G over VI. And if we just plug in the 10 again, the negative 10 for G, we're going to get the velocity of the blue block at collision is going to be V initial minus 10 over V initial. So that's the other velocity you need to keep in mind. So going back, jumping back and forth a little bit here, if we go and look at our conservation of momentum, we're going to plug in both sides. So we know that V initial was that 10 VG plus 10 VB, and then we know that the momentum final is going to be 20 VF. So the VG plus VB is going to be 2 VF because we just divide by 10. We're going to make it a little simpler for us here. And then we're going to plug in those two values we kept in the back of our pocket. We're going to have that VG and VB. So negative 10 over VI plus VI minus 10 over VI. And this is all going to be equal to 2 VF. Conveniently, the negative 10 over VI is going to be like terms. So this combined into VI minus 20 over VI is 2 VF. And this gives us a nice value for VF of VI over 2 minus 10 over VI. This is probably the last value that's super important to remember or write down. So going back, we now can look at what is this distance after. What's this distance after collision? Some of you may or may not recognize this kinematics equation. I would recommend knowing it. It tells us that a final velocity is equal to the final velocity squared of an object is equal to its initial velocity squared plus 2 times its acceleration times distance traveled. So if we just take v squared equal to be 0, because we know that when these blocks are done moving, they should be at their height, their maximum height. We want it to be vertical velocity is going to be 0. It's a very typical projectile motion problem where you know that v is going to be 0 at the top of its trajectory. So plugging in 0 is actually very helpful because we know that v naught squared plus 2gd is going to be equal to v naught squared minus 20d. We're just going to plug in that g for a once again because everything is still under the influence of gravity for this acceleration. This is really simple to solve. It's going to be v naught squared is 20d. And if you remember, this v naught, the initial velocity of these two blocks together, is the v final we found earlier. It's this value of vi over 2 minus 10 vi. The two blocks together are traveling upwards at this speed right after collision. So if we plug this in, we're going to get d is equal to v final squared over 20. So if we look at our blocks, we can plug in this d after value. We know the distance is going to be v final squared over 20. And the math gets a little bit kind of scrambly here, squirrely here. There's a lot of letters and lots of numbers, but you're just going to have to trust the process. It's going to be 1 over 20 vi over 2 minus 10 over vi squared. We're going to do a FOIL expansion here to make it so we only have all the terms separated out. It's going to be much easier for us at the end, you'll see. And getting this expansion tells us that the distance after is vi squared over 80 minus 1/2 plus v over vi squared. So this vi you'll see shows up quite a lot, but it actually is very helpful in telling us what vi actually is. It's not going to be too messy. It'll cancel out very well, I guarantee it. So, going back to our question. If we have this h total, well, we know it's 1 meter. We finally found h collision and d after. We can all plug things in now. We're going to send 1 meter to the sum of those two heights, or distances. So here we are. We got 1 meter is going to be equal to 1 minus v over vi squared, which was h collision, those first two terms. And then the distance after was vi squared over 80 minus 1/2 plus 5 over vi squared. And that was those last three terms. As you can see, you can cancel some things here, which is very elegant. Those 5 over vi squares are gone. So that's really helpful because now we don't have to deal with any vi to the fourths or anything like that if we multiply. And additionally, we can cancel out these 1s on both sides. And this leaves us with vi squared over 80 minus a half is 0. Doing some algebra, or just moving it over to the side, we're getting vi squared over 80 is 1/2. If we take that, we're going to know that vi squared is 40 by multiplying 80 to both sides. And that leaves us with our final answer of the initial velocity must have been square root of 40 meters per second. Isn't that cool? So that's our final answer. And if you got something near this, if you used 9.8 throughout your question, I applaud you. You're much less lazy than I am. But if you were able to get to this conclusion anyhow, you should be very proud of yourself. If you can solve this question, like I said earlier, I think you have a pretty good shot at doing good on the momentum portion. I don't believe it'll be much more complicated than this year. It certainly was not this complicated last year on the AP Physics exam. So I trust that if you had the intuition, you'll be just fine. But even if you didn't, I hope you take this as a great lesson. It's a really fun problem to solve, and I encourage you to find a general solution and let me know about it. Because if you can find a general solution to two blocks colliding and you want them to just reach any height, h, what does the velocity of the bottom block be? And the masses don't matter. They can be different masses. If you can find a almost formula for that, that would be very impressive. So I hope you guys enjoyed this video. I promise the next one won't take so long to come out. And I hope you have a nice night. Thank you for watching.